and not Unity. Okay, so we're recording. Okay, so challenge 2, Team A. Can you briefly tell me, Team A's leader, how is it going? I mean, if you're talking, yeah, go ahead. Just a quick report.
Hello, I'm from Group A, and I have managed to. Everyone is now in a group chat, at least in a line group chat, and we will divide tasks tomorrow. As I was quite busy, I'm quite busy with midterms at the moment. So after the midterms, I will work on Lab on Python and data science, and we will divide the tasks.
But midterm week is next week, right, guys?
Yes, but I have my midterms this week. I don't know why, but
I know, because the professors, they should follow a schedule and they don't. So, understood. Yeah. Everybody has their own. Yeah. You make the rules and then everybody has an exception. Very good. So 4 people, everybody responsive in the line group?
Yes,
did you guys...
5 people are in the line group, actually.
Okay. Somebody brought their parents? Or
yeah, maybe.
It's joking, but do invite your parents to your line group, please. Do you guys read the challenge? Do you plan to meet in person? Are you going to work virtually? Tell me.
I am always I like working together, like to have one meeting in person, but
Okay.
we didn't plan anything yet. We are not really far with challenge 2, or not
Okay.
far at all.
So you haven't read the challenge yet, yeah?
Yes.
Okay, very good. What else? Did you do the evaluation, guys? Please do the evaluation forms as soon as possible. Did you do the evaluation form?
I did, yes.
How was it? Was it smooth? Was it easy to go through it? How was it?
It was good, and I knew sometimes it was hard to came up to the presentations of other groups, but
sorry. What was hard? What was hard?
To rate like your other groups, and the Chinese names are sometimes difficult to find who is who. Yeah.
Trust me, I've been here for 10 years, and yeah, it's no comment there. Yes, but I share the struggle with you, although Chinese names are beautiful. Okay, that's not say anything bad about anybody. Okay, very good. So let me just take my notes. All in a line group. We'll meet in person. We'll meet in person. Form are all right. Forms are all okay. Very good. Okay. Next, let's see, Group B. Guys, can you tell me something, Group B?
Hello, do you hear me?
Yes, we hear you loud and clear.
Okay, perfect. So as I told you, our leader resigned. So I just took the lead like this morning, and I created the line group. So we didn't started anything yet. I just read the PDF and took the information from the subject, and that's all.
Okay, very good, very good. Did you see the forms? Did you fill in the forms?
Yes.
Any comment on the forms? How is it? What do you prefer to watch the video? Do you prefer to look at the report? Do you prefer to look at the code? Tell me a little bit.
The report, personally.
I see. Okay, very good. So yeah, so as I said, usually it's very rare that leaders quit. It's very rare. It usually never happens. But yeah, if you are happy taking over the role of the leader, I think it's okay. And yeah, as you said, we try to eliminate this type of uncertainty and bad experiences for people, but we cannot be too much. Okay, very good. Let me take notes. Swap of leader. New leader is okay. Leader is there. Everyone is in the group. And forms are filled. Very good. Thank you so much. Can we go to Group C?
Hello, do you hear me?
Loud and clear.
Yeah. We got 5 people theoretically, but we only got 4 people. missing one, and I assume he's gonna drop a course. So we got online meeting, 4 people meeting, and split the work. And for the evaluation form, I'm not
Yep.
struggle with the Chinese name. I'm good with it. Yeah, I know all these names.
Yeah,
So yeah, it's pretty good.
yeah, very good, very good. So you do remember all the characters of the names. Very good.
Yeah, I do remember.
I noticed that you're criticizing the instructor of the course, but I'll take the criticism in stride. Yeah, very good. So when you did tell me something. When you did the evaluation, did you watch the video? Did you read the report? Did you look at the code? What did you evaluate?
I do watch a report in the code. Yeah.
What do you base your evaluation on? How exhaustive? How they follow the instructions? How creative? What do you appreciate in the report?
I think the code have to be structured and easy to read. So if I can if I understand the code, I'll give it a higher score. And the report maybe have some form or some chart or something like that. And I'll give it a higher score.
Very good, very good. But of course, the code is all written by ChatGPT, right, or by Copilot. So
Yeah.
can you tell if somebody understood the code from looking at the code, or if they just copy and paste it from Copilot? Can you tell?
Kinda. Because some people maybe just copy and paste the code, but some might do some automation. Yeah.
Yeah, it's very. Yeah, it's a very thorny topic, right? So yeah, I don't want to discuss it too much. Anyway, thank you so much. Group D. You guys can the leader come and tell me something? Yeah, Group D.
And we initially have 5 members, but after I distribute the challenge into 5 parts, one member said he will drop the course, so we just redistribute the challenge into 4 parts, and everyone is still uh, choose what they want.
Very good, very good. Yeah. So when
And
you
that
distribute
member say he will contact you to tell you he will drop.
no problem, no problem. So tell me this: when you because I noticed there's something that you guys tend to do, right? So when you distribute the code, right? Do you have a way to then look out at the code of other people? Because there is for me that I see it in the presentation, right? That when you distribute the work, then everybody's working on their own part and they don't check the part that the others do. So yeah, any comments on that? Can you comment?
You say that everyone focus only on their own part.
Correct. Do you have a way of getting people to just go back and check what the others have done, understanding the rest of the code? Tell me about that.
Maybe I think make the slide for other team member is a good way to let them to understand others' code, because they have to read their code and chart, then they can make the slide.
Understand. Because like if the project, like if I were you, right, I would just have a project on GitHub and then everybody works on the same code on GitHub, but you don't use anything like GitHub to cooperate, right? Everybody writes their own code locally, correct?
Yeah. Oh, on Colab, Google Colab.
Oh, so do you use the same collab page for everybody?
Yeah.
Okay, good. So at least you see what the others are doing. Okay, good. But still, yeah, you're right. It's yeah. Sometimes I notice that you guys don't do an effort, because ideally it should be that you go out, you distribute the task, and then people get together and they discuss the tasks and how they solved it, and then try to improve and to pass the code from one another. But I understand that yeah, you guys don't do anything the first week and then try to cramp everything the second week and then end up doing everything right before class. That's what it means to be a student, I guess. Okay, just yeah, keep in mind. So try to get people to to cooperate on the code. Okay, very good. Group E, tell me something, guys.
Leader of Group E,
Hello, hello.
and all team members have joined the Slack group, and we have roughly divided the work. And next, we will discuss the details of each person's part.
Okay, good, good. Did you fill in the forms?
Yeah?
Any comments there?
No.
Was it difficult? Was it easy to decide? Was it clear who was better than whose? Was it clear?
That's pretty clear.
Okay, very good, very good, very good. Okay, so then let's go back to challenge 1. We had group B that wanted to present. Unfortunately, there was a change of leader. So I think it'll be okay. Yeah, group B, take it away.
Can you see the screen share?
Yes, just a second. I have to do group B and group E. Okay, good. Okay, take it away.
So, anyone do the first page, or we just skip this?
But I just
Okay,
want to
so
know
this
why you copied my name and the name of my lab to your slides. SR is, yeah.
I didn't do this slide. We can just delete this.
SR is my name. Is my name, right? You should put the name of
Change
your
it to Team Link.
Okay, very good, very good. Okay, go ahead.
Okay, so let's just show it. Okay, so this is the KNN report from last week, challenge 1, and this is our group members. We have these 5 group members doing the project, and this team member dropped it out, sadly.
So in this project, we'll be focusing on exploring different variations of the KNN algorithm. The aim was to improve classification performance by addressing class imbalance using techniques like regularization and feature rating. We work with the asteroid dataset from Kaggle, which contains various features like asteroid diameter, albedo, and class to predict the classification of asteroids. So before we could put our hands on training the models, we applied several pre-processing techniques to prepare data. These involving feature scaling by using the robust scaler to minimize the impact of those outliers data. So we can be focusing on the middle 80% of the data of it. And then we also use dimensionally reduction by using PCA. So we can reduce the data into two-dimensional for better visualization that we will see later. And eventually we use stratified sampling to ensure that our class distributions are more balanced, especially given that the asteroid data often involves some pretty imbalanced data.
So what is I hope you can explain stratified sampling. I've never heard of it. So let's see. Go ahead. I'm very interested. Yeah.
You mean the last one?
Yeah. Go ahead, guys. Go ahead.
Do we have this?
No more slides. Hey, I really like the font that you guys chose for the title. It's a very nice font. Yeah, go ahead, guys.
So here by mean the transformation we use the weight-based scaling to apply different ways for features that we will later see in the weighted KN part, and the outlier management by using np.clip to avoid those extreme outliers.
Okay, so we then go into the classic KN algorithms. So this KN algorithm is pretty simple. So we have a model which we don't have to train it. We just need allow it to remember all the data we give it. And then when it predict the target item, it just calculates all the distance from the target item to the data we have stored in this model. And then we will choose the top K neighborhood. So we predict the unknown data to that most group in those K neighborhoods, and we get the predictions. So here we implement the KN from scratch, and then we use it to predict the test data set, and then we evaluate using the accuracy and precision record and F1 score, and then we show it in confusion matrix and some sort of PCA plot. And we have the different K values from 3 to 5 to 7. So we calculate the distance with the Euclidean distance, and then we predict based on the majority votes. And here is our resource from classic KN, and we have classic KNN to accuracy, the highest with K equals to 7, we get 96%, and we have the precision with K equals to 3 to 83%, and which resorts to this is because the larger K will resort to the group to vote the target item to the majority item, so we lose the actual prediction. So we see the F1 score here, the K equals to 3 have the highest F1 score, which means the item is more real than the K equals to 7, because those voters or those neighborhood will just be the majority target.
Can you zoom in the picture for the F1 score?
Here?
No, the icon for the F1 score. Oh, look at that. Look at that.
You mean this small chart?
Yeah. Precision, recall. Oh, that's how they represented it. No, I like the representation because it's represented as a level, right?
Yeah.
Nice. Because the F1 score, it's a ratio. Go ahead.
Yeah, so we have to choose the middle point from precision and also the recall F1. So here is our error rate plot and our score F1 score plot and our confusion metric, which has a line across here, which is the correct ones, the model guesses, and the outer ones are the wrong one. And this is in log scale, so we can see the colors. It's pretty light outside the line here. Here is our classic KN scatter plot, and we can see the groups are basically separate on the upper part, and on the down part here is a more max one. So here we have more wrong prediction, since the majority MBA, I think, is this blue one, dark blue one. So the asteroid around this will be mistakenly voted to be MBA.
Which is the most.
Yeah, which is the most target in this data set. And we go into the weighted KNN algorithm. It's basically the same to classic KNN, but we added weighted to the features. And the calculation is just times changeable or trainable weights on the distance. And since we have some log scale, we will power it, and then we will square it, so we can just time the square weights outside the original distance. And then we train these different ways to find the best accuracy. So basically, we separate the training data, which used to let the model memories all the position and targets, and then we separate 20% of validation data to train the trainable weights, so we get the best accuracy here. And here we will just introduce ways to features and modify the distance metrics. And we also evaluate k equals to 3 and 5 and 7, and we will find the best weights from grid search. So I just let the model to run different type of weights, like 180 times, and then you will choose the top 10 best weights, and then you will just slightly modify the weights to see if we can get it better.
So did you
Okay, so
implement grid search yourself? Sir? Yeah.
Yeah.
Okay, go ahead.
Okay, so here's the result from weighted KNN. We can see the accuracy is much higher than the classic KNN because the model can capture the most important feature, and we also show it here, but it's pretty small. I don't know if you can see the words down here. And
so
then we also have.
The question is that if that's in log scale as well.
Yeah, it's in log scale.
Okay, good.
Oh no! In this feature weights, it's just the weights.
Okay,
The
good.
feature with the weights and the confusion matrix in log scale. Okay, so here we can see the precision and the recall and the F1 score are all higher compared to the classic KNN. We can get the incredibly high 75% F1 score, which we only get like 63 or 65 in the classic KNN. And our classic KNN's accuracy highest with K equals to 7 is 96. And here we can get 97 with all the Ks. And the precision is high in K equals to 3, which means the majority group in this data set is still too big. But we can see the the growth of F1 score after we apply the weighted to the features.
Very good.
And here's the weighted KNN scatter plot. So since the classic KNN1 is difficult to tell the distribution, so I add some light color down here to visualize it, and we also add the text. So here is still the same. The MBA, I think it's the light here, light red. Down here, the MBA here is pretty much. And we have MAO, APO down here. So they probably most of the error prediction is from this part and this part, the dark ones.
And next part is the regularized KN is based on classic KN to handle the situation where some classes have many more samples than others. So we compute class weights based on their frequency in the training set. So the rare classes get higher weights, and we can improve the situation. Okay, let's see next page. We can find we get a little lower accuracy and we get higher recall and we improve the macro F1 score. Yeah. So and this scalar is similar to classic KN because we just adjust the class weights by their frequency, and the scatter is similar. So we can go next part.
Okay, so now I'll do the basic comparison of the results from classic, weighted, and regularized KNN. So as
Sorry,
you can
I
see,
missed a little bit. Can you give me some more details, however you guys remember, about this stratified sampling? So because yeah, can you tell me a little bit? So what is the stratification over, right? So if you sample them based on the frequency, that's something. But what is the stratification from? Guys, in the first slide, right? So you talk about stratified sampling, correct? Can you tell me what that consists of? You just discussed sampling, right? But the sampling that you just discussed was based on the inverse of the frequency. Guys? I see someone is Googling stratified sampling. No. Any comment on this or not? Okay. The guy that just presented, how did you implement the resampling? Just based on the frequency, right? Hello.
I
Yeah.
don't think I have applied the stratified strategy in my data preposition, but I think it's just we divided the data set into smaller one, and we keep the homogeneous subgroup in the data, I think.
I see. So you do, okay.
Yeah, so I know this strategy is for the imbalanced data set, but we don't have applied this strategy to do our data preprocession in at least my part, the classic KNN and the weighted KNN.
I see, I see. And because it's stratified sampling, I understand. Yeah. Okay, no problem. Yeah, because of course, right? If you make it homogeneous, then you're throwing away 90% of your data or whatever it is, right? So you throw away a lot of data, and when you do that,
almost 70% or 78% of the data in this asteroid data set is MBA, and the other 20% is the AOT or ATO.
Correct. So if you have to balance it, then you throw away something like 90% of the data, right? So that was the whole challenge, right? The whole challenge was to try to deal with, well, not the whole challenge. Part of the challenge was try to deal with this. Okay, very good. Go ahead from here, please.
okay, so I'll now compare the analysis for the three type of KNN used. So why we use accuracy and F1 score? Because for F1 score is formed by precision and recall, so there's no point comparing like just purely precision and recall. And from the comparison, you can see that accuracy is generally high for all three kind of model. However, the F1 score is slightly lower at 60 to 70%. This is because of the imbalanced data. However, you can see that after regularizing, the F1 score have improved from classic and weighted. So that this shows that regularization helps with the class imbalance in the KNN. Then for the classic KNN, you can see that the accuracy and F1 score is there's a very huge difference. That's why it shows the imbalance. So for weighted is like the middle where with the accuracy and the F1 score is like optimal and is average from both regularized and classic KNN. Yep. Next slide, please. Yeah, so conclusion is that weighted KNN achieves the highest accuracy and a well-balanced F1 score, so it's like better off for just use purely classic or regularized. So while regularizing improve the F1 score, but it reduced the accuracy by a bit. Yeah, so moving forward, maybe we would like to explore more like regularization techniques, like for example, merging of different kind of balancing method, like using a generative and a removing kind of merge, like smoke plus tomac kind of relation to balance out the data. And also focus more on like hyperparameter tuning where there's like time and space or GPU that allows us to do a full kind of grid search instead of using random search. Because of our limited GPU, we cannot do a full grid search with a lot of K. Yes. So also consider other like testing or classifier like random forest or XGBoost for comparison. Yeah.
Yeah, of course, but this is only one model. Yeah, very good. I think you guys learned a lot from this challenge. I mean, this group and everybody in general. Yeah, so I think it was good. Yeah. Okay, good job, guys. Good job. Very good. Can Group E come and talk to me about their challenge? Yeah,
I mean, we already presented like half of it, so it's only going to be the people who weren't there to present last time. So this is a call out to those people.
And maybe give us a quick rundown also the previous slide so we don't forget. Just
Okay, then I have to open slides quickly. This must be the right one, right? You can see the slides here.
Yep.
Yes. Okay. So last time we introduced the problem. We had an 80% training split, 80-20%, 80 and 20 split of data. Then we talked about implementing the classic one, how where we specifically focused on the different parameters you could use to make your model, and also about how it became more, how we solved the efficiency problem that most people ran into, that you can't just brute force it. Yes, and we talked about the fact that the data set is very heavily skewed towards one class, which everybody else has mentioned. So we had the problem of this one class MBA being too high, which then can be seen in the confusion matrix of the classic KNN, as there are many classes which it cannot predict at all because they are not very frequent. Yes, we landed on a value of k equals 2 or k equals 4 for the classic one being the most well-performing. More plots. Then we talked about the different parameters that you could use to make these models, about like which ones you would probably use, being that the classes we were looking at were orbital, so describing positions in the solar system. We thought that maybe it would be the orbital parameters that would perform best. This was when I had not finished completely with doing this test, so I didn't really have many results, but I can now say after doing it, actually they didn't perform better, even if you made a mix of them. The first mix that I did all the way back to here was apparently the best parameters to
really
to use. Yep. So I can't explain why, because it's a mix of orbital parameters and spectral parameters and diameter. I don't know why. And then we moved on to the weighted KNN, where the people who did the coding on the weighted KNN weren't here, so I think that's where they're gonna start off from.
Okay, go ahead, guys.
But I don't know if they've made let me check actually on the slides if they've made their own slides. If they are even here,
guys. Yeah.
I did text out in the group chat and they said that they were ready, or at least one did. But
let's see. Guys, Group E. While we wait, the new data set, I chose it for the new challenge. I chose it very carefully. It's predicting the score of wine from chemical measurements of wine. So I hope you guys are going to learn a lot about wine and
you're Italian, right?
Yeah, on paper, yeah. My passport says so, yeah.
Okay, yeah, then we gotta tread carefully. Just don't wanna upset an Italian about their wine.
Very careful. You might have to I might revoke your bachelor degree, your high school degree. You'll have to go back to elementary school. You know, if you don't write carefully, yeah. You might want to skew the model on Italian wines and versus French.
I did already look at some of the parameters, and it said that adding citric acid in the EU is prohibited. So maybe you can find out that the ones with low citric acids are the best, meaning they are from EU, and then maybe Italy.
Nice. That's a good. So that's how they control acidity. Yeah.
Okay, let me check something.
Yeah, Group E. Maybe you lost some people. Yeah, somebody else from Group E is here. We move on. Okay.
One guy has exited back, but I don't know.
We can give them some time. We could come back later.
Yeah, okay. I'll have the slides ready.
But you did a good job for sure. And yeah, also your comments on the parameters are good.
Yep. So I'll be presenting the part.
Oh, okay. Good.
So you're here.
Okay,
go ahead.
Yeah, I'm here. Yeah. So here's our big picture for our regularized KNN. So we started off with a flexible classic KNN that can use either plain Euclidean distance or weighted L2 distance so that the features don't count the same. And we can also choose to turn weighted voting on or off. Follow that, critically, instead of spitting out labels, our model return class probabilities for each test points, and we need those probabilities for the next step, which is the balance decoding, which will shape the final label allocation. So we think of it as first estimate how likely each class is for each point, and then in this separate step, we will decide the final labels in a way that respect the overall class balance we expect. Yeah, next. Yeah, so to get good distance, we'll learn feature weights. We'll use a Dirichlet-driven search to generate many candidate weight vectors that live on the probability simplex. For each candidate, we'll train a KNN, score it on a validation split, and keep the weight that maximizes accuracy. This is a lightweight yet effective method where the features that actually help discriminate get higher weight, while those noisy or redundant features get shrunk. The result basically
Wait a
is
second, let me think about this. Wait a second.
Sorry?
So you randomly generate the weight combination, yeah, from the Dirichlet distribution. Then you do validation accuracy.
Yep.
And then you just keep the one that performs the best, right? In terms of F1 score accuracy, because that's part of the trick, right? So what do you try to maximize here when you do the selection?
Because
you understand, right? So this is because here. So here you balance the dataset by you balance the dataset, right?
Yeah.
Correct. So so accuracy in F1 score should be okay. I just want to make sure. I mean, yeah. I just wonder which one did you choose? If you chose accuracy versus F1 score. Yeah.
I chose accuracy.
Accuracy.
Okay. Yep.
Yeah, because the dataset is balanced. Yeah. So. Okay.
Yeah. Okay.
And then random weight generations, right? So. Okay. Good. Go ahead.
Okay. Next slide, please. So for balance decoding, our KNN is actually notorious for following the majority class, where our balance decoding step fixes that by aligning the final predicted class count with the training pairs. So basically, we'll take the probability matrix from the classic KNN and the target class proportions, and we assign labels so that the total number of predictions per class matches those proportions, with a small epsilon to avoid numerical edge cases. Basically, with the intuition that if class C should have 15% overall, the final label for C should be approximately 15%, focusing on the samples where P says that C is most plausible. The trade-off is quite important, where it tends to leave recall and F1 for rare cases, but it can reduce raw accuracy if the test distribution isn't identical to the training distribution. Yeah. Yeah. Next. So on the last part, I actually tuned the grid search CV over K and distance type and whether to enable weighted voting and then evaluate it with accuracy and F1. So on our run, our regularized KNN landed around 80% accuracy and 0.81 of F1 score, which confirmed that we are representing rare classes better, but we gave up some accuracy on the dominant class. Yeah, so perhaps our regularization step was too strict. Yeah, that's our findings.
Do you have the plot of the weights that you found with this? Because K is very large, right? But of course, we don't know how quickly the weights decay with K. Do you have a plot of the weights?
No, nope, I didn't generate a plot.
Next time, remember, right? Because like if you see, so K is equal to, yeah, you understand what I mean, right? I just want to
Yeah.
see.
Understood. Yeah.
Go ahead.
Yeah, that's all my part. Yeah, that's the last slide.
That's it. Yeah, because accuracy and F1 score are pretty good. Yeah, pretty nice.
Okay.
Okay, very good, guys. Very good.
Yeah, the last guy has not.
Okay, go ahead.
Texted it. No, the last guy has not texted anything, so I don't think we'll be talking about weighted canon that we didn't talk about last time.
But do you have the slides? No.
I mean, yeah, I have the same slides as last time, which there was a
Nice.
person who went through. So.
Okay, no problem. Understood. Just good. Okay,
Yeah.
so good job, guys. Good job, guys. Let me just take my notes. Very good. For one guy, very good. And good. Okay, guys, I suggest we're a little bit early. I suggest we take a 5 minutes break because after this we're gonna go into the early PCA. So let's take a 5 minutes break, walk around a little bit, and then when we come back, we do a set of slides on PCA. Okay, guys, I'll see you back in, let's say 4 minutes. Okay, 4 minutes. We're back here at 14:10. We start over. Okay. Okay, guys, very good. So slowly, while we wait for everybody to be back, we move to PCA finally. View full screen. Are we already full screen? Where is my full screen mode? Finally, we discuss PCA. So many of you already encountered PCA in your reports, but now we can discuss it a bit more in depth and do a little bit of more theoretical discussion behind PCA. So for the engineers in the room, PCA is just SVD. It takes a while for your brain to connect singular value decomposition and this idea of the most informative projection. Also, we will not go through some of the variations of PCA that are relevant to people and some of the techniques that are behind the evaluation of PCA. So the one aspect of PCA that we're not going to discuss here is the computational efficiency, right? So in the other class that I had to cancel because nobody took it, we would have done the numerical methods for calculating PCA and argued that PCA is numerically very efficient. But I'll try to give a different name to the class for next year and just try to reoffer it. But yeah, basically, PCA is by far the most widely used, let's say, machine learning algorithm outside of the realm of data science and machine learning. So whenever you talk to somebody, even if they do chemistry or psychology or whatever you can imagine, they will most likely know PCA and use PCA daily in some cases. So let's go through this, right? So just a second, guys. Why are we here? Introduction to data science. Okay, so just a second, guys. One moment of, yeah. So interaction terms in unique parameterization, big data, and high dimensionality. So people often talk about the course of high dimensionality. Then we'll discuss PCA, then PCA for regression, which is PCR, and then PCA for imputation. This is something that we'll also touch upon. Remember, imputation is when you try to fill in missing data in your data set. Okay, so let's go back to the discussion on interaction term and unique parameterization. So there is this beautiful data set, very present data set, which is compares the taxi and Uber rides in New York City. So you see the data set here. There is the drop-off latitude and longitude, the fee, the fare amount, the time elapsed between drop-off and delivery, and so on and so forth. This is a public data set that has 1.9 million taxi and Uber trips, so 1.9 billion rides, right? So a few years. And each trip is described by 23 unusable predictors, okay? And you have one response variable, okay? So this is the data set. You see that the entry is 1.9 million mostly, and then we have 30 features, and these are the features. So what we want to do in this case is that we want to find the fare, right? So we want to predict the fare. And because let's say that Uber pays us a certain amount of money to figure out how to set the price of their fares. So then we start going through the techniques that we've seen so far. Of course, we choose linear regression because it's the one that we like the most. It's computationally efficient. And we get to this point in which we exhausted the increase in accuracy we can achieve by adding one of these 30 features. So we start adding in interaction terms. So remember, the interaction term correspond here to the case in which you consider the product of two variables, right? And the way in which you deal this in a linear regression framework is that you consider x1 and x2, x1 times x2 to be an extra variable in your data set. This new variable doesn't have a linear relationship with x1 or x2. right? So there is no particular issue when we talk about collinearity and stability of the prediction and so on. And let's say that X1 is a binary predictor, which indicates whether the pickup was an Uber or a taxi, and X2 was the length of the trip. And as we said, Y is the fare of the ride. So we discussed this already. We can look at the parameter B3 and we can see how this can be interpreted. And this, we said, is as if we are switching between two models depending on the value of the binary variable. So we could go through this exercise and we can come up with a lot of possible interaction terms, and then try to improve the prediction by adding these interaction terms. Okay. So the idea is that when we're trying to with this prediction, we want to always include the main effects, and the main effects will be, for example, the variable themselves. And then we ask, well, the main effects might not always correspond to all of the input features of the model. Maybe there is some aspect of the prediction which is not some aspect of the input variables which are not relevant to the prediction. Let's say that one of the features was I don't know, the color of the taxi, right? Maybe this doesn't play a role in the likelihood that you pick up a taxi, right? Or some features like that. So then the question becomes, what type of model will it make sense to consider, which include the interaction term but not the main effects? Okay, and so let's see here. So we said that once we have an interaction term, this will correspond to the following, right? It will correspond to a model that changes depending on the value of the binary variable. And this one here is a model in which we have enforced the interaction term, right? So in this model, we remember that B1 is binary. Let's say that whether the length of the trip was longer than 13. And here we had considered the interaction term in which we have the length of the trip times the other variable, which is whether it was longer than 13. Okay, so as we discussed, there are many different possible choices of interaction terms. So this is calculated as follows. If we consider interaction term with only two different variables, then this will correspond to P over 2. P in our case is 23. So we have a few hundred of interaction terms considered 2. Of course, nothing excludes us from considering 3 interaction terms, so that we can have some more complex behavior and let's say a model which depends on like larger degrees of freedom, so that we can capture more compelling effects. And the three-way interaction terms will correspond to P choose 3, right? Because it is as if you are choosing 3 variables out of the P in order to create the three-way interaction terms, and then you can keep doing this. And if you remember your beautiful binomial theorems, if you consider all possible interaction terms, that this will be the summation of P choose K for K between 0 and P, and this is equal to 2 to the power of P. Our P was 23, so we have 8.53 million possible models that we can consider by considering all possible linear terms and all possible interaction terms. Of course, this is not very useful, and we will not be able for us to just inspect the models because the numbers are so large. But there is also the other difficulty that in order to determine what will be the parameters of these models, we will only have 100K observation in each case, right? And so, and so things are just not identifiable from this perspective. Okay. So how are we gonna deal with this? So of course we could just increase the number of observation, which doesn't really make sense because as we said, collecting data it's a very costly operation, and we already have 1.9 million models. The more data we collect, the harder it is to train the model, the longer it will take, the computationally expensive it is. So not really the answer in this case. We could try to have some expert opinion, right? So we could call somebody that does urban planning, and we could help them to identify some interaction terms, right? So we could refer back to an expert. Or we could try to do something more appropriate for this, which is to do dimensionality reduction, right? So we want to reduce the dimensionality of the variables of interest using principal component analysis as the example that we see today. So maybe before of your time, but before people started talking about machine learning, people were talking about big data. By which people refer to the fact that in the world that we have now, we have many sensors that can collect a lot of information, and so people realize that there are few regimes, right, in which one is interested in when describing the size of the data. Okay, so let's say that we have two numbers of observation. There are two numbers that we want to discuss. One is n, the length of the data set, the number of observation, and p is the number of predictors that you have. Okay, so it's clear that there are cases in which n is big and p is small. So the case that we just saw, for example, we have the n is 1.9 million possible writes, and p is 23. So this is the regime in which n is big and p is small. Then there is a case in which n is small and p is big. Okay, what is some of these cases? This is something that you encounter often, let's say, in medicine or biology, and it will be, for example, the case in which you have a rare disease, and when a person has that rare disease, they do all possible type of exams because we are interested in understanding scientifically what is happening. So you have you have very few people, but you have a ton of data for that. And then, of course, you have the case in which the n and the p are roughly the same. Good. So when the sample size is large, this is typically not much of an issue from a statistical perspective, just from the computational perspective. So, of course, in the case in which we have 1.9 million, we can talk about linear regression, and we can talk about inference method and so on. And of course, the issue is more computational because the larger the data set, the longer it will take to train the model. So far, we've seen only models which are relatively computationally efficient. But you can imagine that you could have, for example, a deep neural network with a lot of neurons where backpropagation takes a few seconds. And so in the case, it's clear that the computation grows up very quickly. And if we want to account for the computational complexity, what we could do is that we could do some preliminary steps to reduce the reliance of the training algorithms on a large set of data. Sorry, guys. So just remember that even if you have a lot of data, that doesn't mean that all your problems are solved. This is something that we discussed already. There is the garbage in, garbage out problem. So if you have a lot of data, but you don't know how to ask the proper question, or to choose the proper model, how to do the proper validation, how to do the proper tuning, then it's still there's still nothing. There's still no substitute for meaningful inquiry on the data. Okay, the fact that you have a lot of data doesn't mean that you will not run into the problem of not asking interesting questions. Very good. So when P is big and n is small, then we have other issues that we have to address. Of course, conceptually, it's very tricky because statistically, you know that some of the conclusions that you might come to, they're not reliable simply because n is small. Let's say that you're taking mean variance, some sort of distribution fitting, then you know that you don't have n large enough to be able to reliably extract statistical quantities. And you also have some computational complexity issues, such that if you're doing linear regression, then the pseudo inverse that will not make sense, and for sure you're going to have multicollinearities. And of course, the problem of them all, which is overfitting, right? When n is very small, then it's very easy to overfit because your test data is small, and increasing the cardinality of the test data will come at the cost, at the expense of the training data, and so a really bad situation. And this situation is what usually people refer to as high dimensionality. And you need to account for this when you do data analysis and modeling. And which data? Sorry, guys. Okay, so now we can discuss a little bit what to do when you have high dimensionality. So as we said, this is the case in some specific fields, but in general, right? We can say that we have a high dimensionality problem when the number of parameters exceed the number of observations. Okay, so this is the case that we saw before, in which we had 8.3 million possible models to choose from. We only have 1.9 million of rights, so we didn't have enough rights to allocate to this problem. For example, some example that we saw already, where we don't have to change the field that we are referring to. So let's say you are doing polynomial regression, and you have a large number of polynomials and a large number of predictors. So then number of parameters grows very quickly. For example, when the predictors are genomic markers, right? So you have the certain presence or absence of certain genes. Every person has millions of genes. So as we said, computational biology is the case. Another case is NLP. Okay. So for example, you are using a bag of word type of approach to language prediction or to language generation. Then of course you have a few million of English words, and maybe you are dealing with short sentences that only have 10 characters each. Then how does a scalar handle unidentifiability? If we have an overspecified model, that's another way to describe the case in which P is larger than M. Then we only need n-1 predictors to exactly predict every possible observation in the case where we have no noise. So this follows from the invertibility of a linear system, basically. So what happens to the extra estimates is that the model will just throw them away, or and try to choose a subset of unique input features. But this of course makes sense only if we believe that we are observing a pure linear model under no noise. And so in reality, this will not happen. But you can do a simple try, right? You can try to do a linear regression using the age. And what are we doing here? And yes, no problem. Yeah, so this will create an instability. And so now we can move more formally to our PCA and try to describe a PCA as from a more formal perspective and more mathematical approach. So let's discuss this. Okay. So let's say that we have a certain set of features, and these features are the Z1 to Zm. So we have M of those. And each of them are a linear combination of the P original predictors. And so the index for P is the J index. So we said that the Zi features are a summation of a certain coefficient phi ij multiplied by xj. Zi iterates from 1 to M. Zj iterates from 1 to P. And the phi ij, they iterate from 1 to M and from 1 to P. Okay, of course, everything is more beautiful when it's expressed as a matrix. So you can say that the matrix Z is equal to a phi matrix multiplied by the vector xj. Very good. And with this feature, with these z features, what we want to do is that we want to build a linear predictor. So we believe that our observed variable y, let's say again the fair, maybe in the Uber dataset, is equal to a set of coefficients b0 to bm multiplied by our z0 to zm plus vector noise epsilon. And what we want to do is that we want to determine the coefficients beta. Okay. Very good. So again, let's say that we have n observation and p is larger than m. P is larger than n. So we want to define a set of features, m, right, such that m is less than p, so that our linear model is fully specified, and we can write a linear predictor that makes sense, in which we predict from the intermediate features z1 to zm all the way to the y. Okay? Good. So x is the original input, zi are the intermediate features, y is our label. And we want to write the linear predictors. We want to write a linear model from the z's to the y's because we have too many xj's. Okay, very good, very good. Now everything is in place. Remember that P is the total number of input features x, m is the number of intermediate features z, and we only are predicting one scale. Okay. Very good. So we are somewhat there. Okay. So we know we are somewhat on the way. Then we can ask, what is the optimal predictor set, right? How can we define the optimal predictor z's in order to improve the performance of our final linear model? So the idea is that you will want to choose the z's in a way which does not depend on the y label, right? So, and why would you want to do this? Because sometimes when you collect data, you will want to have an unsupervised approach, right? In which you decide how to represent the data to the intermediate feature z, which does not depend on the label, but depends on the nature of the data itself. Okay, good. So, of course, we cannot do a grid search as you guys did in this last case, because there are many more features than the one that you guys considered. So introduce PCA, our beloved principal component analysis. And the idea is as follows, okay? So we want to determine a small set of predictors, which is a linear combination of the original data that captures the maximum amount of variance in the observed data. So all the keywords are there, right? So we start from a high-dimensional data, so P very large. Usually, when we do PCA, we like to do PCA for dimension 2 when we want to generate the plot, meaning that from whatever high dimensional we have, we want to project the data down to 2 dimensions because we live in a 2-dimensional world, and so if we live in a 3-dimensional world, our screen is 2-dimensional. So we want to represent the data in 2 dimensions so that we can plot it in our screen and print it on our paper. And the key word here is the maximum amount of variance, okay? So the idea is the data has a certain variability, and you want to project the data on a low-dimensional plane in order to preserve the essential character of the data. And you could argue that the variability of the data is the essential character, okay? So if you have a feature that never changes, then in a sense, you don't want to preserve this feature because there cannot be no information, regardless of the downstream task, on the that depends on this variable, because this variable doesn't change, right? So if something doesn't change, it means that they are not revealing much information, and so it's not very crucial for you to capture it, okay? So when you capture something, there is this idea of energy, right? If one certain variable has a large variability, as if it has a large energy, so it reveals a lot about it reveals a lot about the underlying phenomena that generated the data. Okay, so remember that this variance aspect is crucial in the following, right? Very good. So now we have all the ingredients. So we want to generate a Z1 to ZP. We want them to be linear combination of the original predictors. Why? Because linear operations are fast and efficient, so it makes sense that we want to have a linearly dependent from the original features. Now comes something important, which is we want these features to be pairwise orthogonal. Okay, so we want these Z's to form an orthogonal basis. And here there is an idea that the original predictors, the original inputs to the model, they are not constrained to be independent, and so in a sense they are naturally redundant. Okay, so because they don't, they share some common information by the fact that they are not orthogonal. Okay, so they are so high in dimension because they have not been structured to be independent from each other, in a sense. Okay, so you might ask yourself, why is orthogonality important here, meaning that they could be related to some nonlinear function. But of course, the assumption of linearity is an assumption that we always do because it gives us both a simple computational algorithms to treat things, and also it's conceptually easy to investigate, and we can build a beautiful theory of these linear systems, and we can understand a lot about this, about the world, if we approximate the world to be linear. Let's put it this way. Okay. So this is everything that we need. Just one last thing, right? Is that we will be happy if we further order the Z's from the highest variance to the lowest variance. Okay. So we just say that the Z0 is the one that captures the largest direction of variability, and the Z1 is going to be independent from the Z0, and it's going to be capturing the second largest variation of the data. Okay, good. So now we have everything in place, and we can go forward from this. So how do you picture this? So here you have PCA1 and PCA2. So what you do is that PCA1 and PCA2, they form a direction, right? So what you do is that, let's say that here the dimension is, just a second. Huh? So the idea is that, what do we want to argue here? So here you have the one principal component, the second principal component. So in this case, right, so that we have two input features and two PCA components. Okay, so this is, let me go back one more. Okay, so let's try to have a visual representation of PCA. Okay, so in order to have a visual representation of PCA, we are going to look at two-dimensional data that is projected over two PCA dimensions. So this is a little bit dumb, right? Because this is not high-dimensional. But of course, it allows to represent everything in figures, so it makes our life easy. Okay? So we start with this x1, x2 on the x-axis, on the x and y-axis. We have x1, x2, we have two-dimensional data. So each point here is x1, x2, and it's an input data of our dataset. For the purpose of this example, we're going to re-parameterize this data as PCA1, PCA2, and we're going to represent the PCA, the composition of this data. Since we start from dimension 2 and we end up in dimension 2 after PCA, there is no loss of information. So in general, right, the projection from the input data to the PCA for the dimensionality reduced PCA will be lossy, meaning that we lose some information of the original data. Since here we have input dimension 2, PCA of dimension 2, it's a one-to-one mapping, and so there is no loss of information. Very good. Okay, so somebody gives us this x1, x2, and then we're going to show you why we're going to have the PCA component 1 be in this direction and PCA component 2 be in that other direction. Very good. So first thing that we do, right, we want to consider all possible hyperplanes of dimension 1 that cut through the data, and we want to project the data over this direction. Okay, so Here we are in 2 dimension. We are looking for a single hyperplanes, which means that we are looking for a line. And what we do is that we project the points over the line. If you remember your high school, right? What the projection is the closest point along this line to your x value, x1, x2 value, right? Such that the orthogonal line from the projected point and the point is so that the distance between the projected point and the original point is orthogonal to the line. Okay, so this is a subset of the original data, right? And for each data, we project the data over the line. And then what do? We look at the projected points and we look at the variance of this object. And then we change the orientation of the line and we keep doing the projection until we find the direction that has the largest variance. Okay. Then we're going to repeat this for the second dimension. And we're going to end up that the second dimension will have a lower variance. It has to be orthogonal from the first one. And this is going to end up our PCA projection example, where we start with x1 and x2, and we perform PCA, and we obtain a reparameterization of the data as PCA1, PCA2. Okay, good. So the math behind PCA. So this is, as we said, it's just a reformulation of the SVD, singular vector decomposition. So this is what we want to do. So Z is our data set, right? So it has n rows and p columns. Okay, and in each column we have the Z1 to ZP. Okay, and this corresponds to the PCA vectors. Okay, so n to p, n are the rows, p's are the columns. So the Z1 to ZP are going to be columns, and these are going to be our intermediate features. How do we obtain these intermediate features? We obtain them from the original input x, which is n times p, multiplied by a mixing matrix, which is the omega p times p. Okay, so notice here that the m is equal to p because we are doing linear algebra, and we just want to say that the full PCA, let's say the invertible case, is the case in which we choose m equal to p, so there is no loss of information. And we can just look at this from the math, and then we're going to explain later what happens when we go from p to m, so we do a dimensionality reduction. So if there is no dimensionality reduction, then the z is going to be n times p, the x is going to be n times p, and the w is going to be the p times p, which is what you would call a mixing matrix. Okay. So when we look at the solution of the problem, so we look for all the constraints on Z. So Z have to have a variance which goes from the largest to the smallest. The directions, the Z1 to ZP have to be orthogonal, and the transformation has to be linear from the X to the Z. Then we have that the way in which we must construct omega in order to be the optimal mixing matrix is as follows. So P has to be such that the columns are the eigenvectors of the square matrix X transpose times X. Good. So notice that X is n times P. So X transpose times X as dimension as follows: P times n multiplied n times P. So n times n goes away. So this is the common dimension in the matrix multiplication. So we're left with a matrix which is P times P, right? Then what do? Is that we do SVD of this X transpose X. This is going to give us the left eigenvectors and the right eigenvectors. But X transpose X is going to be a symmetric matrix, of course. And so we're just going to have singular values instead of eigenvalues and eigenvectors. And so what do is that we take the single eigenvectors and then we stack them all together. They're going to have, each of them is going to have length P. If we assume that there are no zero eigenvalues, then we're going to have P of those. And this is how we're going to capture our matrix omega. Then we say that Z is equal to X multiplied by P. Very good. Any questions so far? Very nice. Good. So you can implement PCA by yourself, and this is going to be the recipe. So first of all, you have to standardize each predictor, as you usually do, right? So you do mean equal to 0 and variance equal to 1. You do this simply because you don't want to carry around the constant terms, right? So of course, if you want to carry around these constant terms, you can add a feature which is all 1 and push all the means to this all 1 feature. Not very interesting, so let's drop it. And then we normalize the variance to 1. This is also clear, right? Because if you don't normalize the variance to 1, then the decomposition will have to be adjusted for the amplitude of each of the single variables. And let's say if you just scale the data, the scale data will result in different PCA vectors, so depending on the scale of the data. It's just a waste of time. So let's just set the mean to 0 and the variance to 1. Then this is going to give you a sort of a scaled input features x. Then you do x transpose x. Then you do the SVD decomposition. When you do SVD, the eigenvalues are going to be ordered from the largest to the smallest. Okay, and then you use this to construct the matrix omega, and then you obtain the z by hitting x with your omega. Okay, very good. So as we said, very efficient numerical methods to do this. Cholesky decomposition is one of these. Householder projections is another one. Interesting numerical recipes to do this. And as we said, this is going to give you, okay, so this, you guys already did this part of the code. It's no problem. And then, and this is the case in which you obtain, let's say, a one-to-one mapping, right? So the Z is a full transform of X. If you want to have a dimensionality reduction, so you want to go from P down to M, what do is that you just keep the largest P eigenvectors, so that then your matrix omega, the first M eigenvectors, so that down your matrix omega will be P times M, so your X times omega will be a N times M matrix, and this will correspond to the dimensionality reduced transform of the data, so that you just keep the M component that have the largest variance. Okay, good. So then this is the plot that you guys all do, which is as follows. Let's say that you're doing a classification task. So this is the data set where you have the heart data, and you're trying to predict whether a person has a heart attack or not. So if you remember, you had a bunch of different predictors: the age, the sex, whatever. And what you do is that you take all those features, you do PCA after normalization, and then you obtain only two PCA dimensions, and then you project your high dimensional data over these two components. So everything now becomes a PCA1, PCA2 type of data, which you represent in a scatter plot. And what you do on top of that is that you add a color which depends on the label, whether they have a heart attack or not. And then you go and you inspect this plot to see if the data can be clustered. Meaning, if you didn't know whether a heart attack or not, right, you could still go and see if the data had the two specific clusters that showed up when you did PCA, meaning that if there was a direction of the variability of the data in the in two PCA dimension, that would have allowed you to separate the two classes without knowing the label. Okay, because then if you go and you add the color corresponding to the class, then this reveals a specific pattern in the data. You could have said, oh, these two clusters belong to these two different labels. So I would have been able, right, using PCA to discriminate the two data, given that they form some specific pattern in the PCA space. Okay? Of course, this is unsatisfactory because maybe the cluster appears in 3 dimension, in 4 dimension, in 5 dimension, and you could still do a 3-dimensional plot with 3 PCA components, and then you're there with the mouse trying to find the point of view in which you can separate the data. But you understand what I mean, right? So, of course, it's easier for us to identify patterns on 2D images, so that's what we usually do, since we live in this universe. Very good. Okay, any questions so far? I hope you guys are okay. So the idea now is that we go back to the regression. So remember that now we want to form only M prediction and use this M prediction for the linear regression model. And the way in which we form these components was irrelevant of the downstream task. So then we can go and apply linear regression on the Z components that we have obtained by just looking at the variability of the data and build a linear model on top of that. Okay, so this will be easy for us. So some notes about PCA. So PCA is what people call an unsupervised learning approach. Why unsupervised learning? Because the way you construct disease is without knowing the label. And this is very appealing for multiple reasons, meaning that you could transform the data to discover some patterns, as we discussed before. Let's say that you want to see if there is some particular clustering of the input data, regardless of what the meaning of this clusters is, and you can use this for discovering pattern in the data. PCA is not good because it's not fully interpretable. Okay, so if you're trying, if the issue is as follows, right? So in a certain PCA component, you still see a linear combination of features, and you could be like, oh, this weight of the input feature in this PCA component is very large, so it means that this particular feature is very relevant for the construction of this PCA component, and this will make sense to you. The issue is that if you have, let's say, 10,000 different input features, and the way in which they get mixed into these PCA components, it's not particularly extreme, right? It's not particularly revealing. Then it will be hard for you to say, well, the PCA component one, it's 1% of these features plus 1% of the other feature plus 7% of the feature. It doesn't really give you much interpretation of how what these PCA components correspond, right? So in some cases, looking at the coefficients of the PCA components will reveal something very fundamental to you. And sometimes you look at the PCA components as just a mix and match of many different input features, and it's not really clear what these PCA components correspond to. Okay. So this point, let me just specify it a little bit, right? So this depends application from application. Okay. So there are many applications in which the PCA components corresponding to a certain latent space, which is very meaningful, but in some components this is not the case. Okay. Good. So, but PCA components is also very useful for reducing the dimensionality of your input data. Of course, if you cannot even represent your input data, then it's very hard to do anything with it. So as we said, it can help you identify visually, right, some features, and also improves collinearity. Okay, so that's also very important. So let's say that we discussed multiple times how linear models are very sensitive to collinearities when there is a implicit linear relationship in between the features. So if you want to pre-process the data using PCA, then you will be sure that the input, the resulting features, these intermediate features, will be orthogonal, and that's the best case to reduce collinearity, right? So if everything is orthogonal, then in a sense every feature brings some new information to the model, and there is no collinearity. Okay. So when you do PCA with Python, as we said, Python is a very high-level programming language. So there are many things that go on under the hood, right? So there are many different metrics and techniques and evaluation tools that are used to perform PCA in Python. So if you call this dot summary to see the results, you will see the model they will use. What was the R-square? What is the F statistics? What is the log likelihood? What is the area under the curve? The residuals? Which optimizer was used? So the technique has been evolving for I don't even want to know how many years. But basically, this technique has been evolving for a long time. So there are many different theoretical results and practical algorithms that one can use to evaluate PCA and determine the quality. Very good. So now we can discuss PCR, right? So which is when you do the prediction, okay? On top of the PCA. So this is plot, right, of the beta coefficients. So the coefficients of the linear regression. So you do PCA. You have on the x-axis you have the number of PCA components. On the y-axis, it tells you for that many PCA components what are the coefficients, what are the beta coefficients that you're going to use. Very good. So here it's you don't standardize the prediction in this particular case of PCA because the last point that you have will be the point where you just take the straight data as it is, so you have linear models. And you see here, right? So when there is no compression, then you have these beta coefficients for the ECG, the rest ECG, the cholesterol level, the sex, the age, and so on and so forth. Then if you use 7 PCA components, what you can do is that you can go and calculate again what are the resulting coefficients when you combine the omega matrix of the PCA and the B vector of the linear regression. You can find the coefficients, and you can see what is the some of the coefficients are set to 0 when you use fewer PCA components in order to do the regression. Okay? And basically, the story that this is telling this is that the weight drops very, very quickly, right? For some of the coefficients that do not contribute much to the prediction. So, for example, if they have chest pain, never really mattered much. And then, as the number of PCA components is reduced, then you see that the cholesterol level becomes very important for the prediction, and then it drops, and then this FPS, I don't remember which parameter it is, but you understand the story. Huh? Now, let's redo the standardization, and let's compare the parameters after we standardize the PCA components. And now we have a clearer plot, meaning that the importance of the features now it's calculated across this normalized feature, so the amplitude doesn't change so greatly. Like the PCA, the beta coefficients are not catching up with the variance of the model, and what is it? What did I go? What happened? Yeah, sorry. And so so you see here that the variability in the feature space it's fewer. This is to say that it's always good to normalize, because when you normalize, you get a more consistent story when it comes to the relevant importance of the features. Very good. A little bit of intuition under what is the underlying mechanism of PCA. The idea is that you start by finding the direction which has the great ability of explaining the variability of the data. The data is inherently centered in the middle of the space because you have normalized it to mean 0 and to have variance 1. And the way in which you find this is that numerically will be by iterative procedure, meaning that you start with the data. When you project over one dimension, you're reducing one of the dimension. Then, having removed the dimension from the data, you repeat another time, and you keep repeating this until you get down to to 0, basically, and you have found the full PCA decomposition of your data, and this explains all the variance from the component that captures the most variance to the component that captures the least variance. Very good. Again, so this is this is a two-dimensional data projected in two-dimensional directions, right? So notice that here the data is not centered, although it should be centered. So you start with the first projection into one direction, you rotate this direction around, right? And you project, and then after you project, you look at the variance and you look at the direction that captures the most variance. here we go into something which is a little bit more experimental for us. And this is just to give you an idea of the mechanism. So bear with the headache of looking at the three-dimensional plot. So now here we have a three-dimensional input data, and it's projected onto two dimensions. Okay, so you have one PCA component and a second PCA component. So what you do is that you take the data and you find the eigenvector. So the purple here is the original data, right? So you find the eigenvector and the eigenvalues, and then these are orders by the magnitude of the eigenvector or eigenvalue. The first eigenvalue, second eigenvalue, third eigenvalue. Then what do you do is that you project the data onto on the first two eigenvalues, and the first two eigenvectors, sorry. So this is the first eigenvector, and this is the second eigenvector. And so the data gets projected onto this plane, and this is what gives you the PCA decomposition of this. Okay? So these two objects will give you the direction. So the idea is that we start with capturing the largest variance, and then we just take a number of components which explain the amount of variance that we want. So generally, you have a very steeply decreasing curve of the explained variance in the data, and as you go down, you will see that the explained variance drops very quickly. And usually, people take a number of PCA components which corresponds to, let's say, 90% of the explained variance, and this is, let's say, usually using maybe 30% of the original dimension, 40%, 20%. This depends on the inherent sparsity of the data that you're dealing with. So some rule of thumb is that a dimension, a reduction of the dimension of 20%, 30%, it's something that one can expect. Very good. So let's go back to the discussion of imputation. So we can use PCA for doing some nice imputation. So the idea is that somebody gave us this data, and we had data that had this missing variable x1 and x2. And what we started by doing is imputing to the mean. Imputing to the mean means that we filled in the missing value with the mean value for that feature. And if we have imputation to the mean for x1 and x2, then all the points in which we had one x2 but no x1 will be imputed to true x2 and mean value of x1. This corresponds to this line. For all the points in which we did have a true x1 but we didn't have an x2, then we will fit the x2 parameters to be the mean. And so this will be a line in that way. And it's very clear that if you look at this data, before and after imputation, you have introduced a pattern with imputation, which is very undesirable because the model that then you're going to go and construct will somehow pick up on this underlying pattern of imputation and might skew the results that come. Of course, we said, well, we could build a model that is used for imputation and use this model for building imputed values, and we could add more fewer parameters. We could have a number of imputation value depending if x1 is missing, x2 is missing, x1, x2 are missing. And basically, we were there saying that it's becoming a huge task because we have a number of models which grows exponentially with the number of features that we have, right? So not very nice. So when we have many predictors and observation, and they have similar values for all of them, then we can use PCA to do the imputation. So we can do this iterative PCA algorithm for imputation. Follow up, guys, because this is beautiful. Good. So let's say that we start with this. Okay. So we have our x1 and our x2, and then our x2 is missing at the first entry of the dataset. Then what we do is that we impute this to the mean. So imputation to the mean is our first step. And then after we've done imputation to the mean, we can form PCA on the entire data and transform and project, right? These points on the most informative direction, which will be the first PCA component. And then we can see what is the position of the imputation into this projected dimension. Very good. Then what we can do, right, is that we can project back, right, the point on the PCA project. We can project back from the, so we have an original imputation. We project on the PCA dimension. This will give us a value of the x2 variables in the PCA space, right, in this projected dimension, and we can then project back to the original coordinate x2, and then this will give us an imputation update. Then we repeat this procedure, so we do PCA again using the imputation update, and this will update the direction of the first PCA components, and then we can again back project into the x2 variables, and we can repeat this until we converge. And this is what we observe here, right? So we started from this, and that, and then when we did the PCA at the last time, then the projection of the PCA onto the projection of the imputation onto the PCA didn't change the direction of the first PCA component, and so we keep it. Okay. So what is the idea behind this? The idea is that the imputation didn't change the PCA direction of the data. And so in a sense, we kept the most informative direction as it should have been if the imputation was not present. So it's a sort of an equilibrium point, right? So the iterative algorithm is as follows. We initialize the imputation to the mean, and then we repeat until convergence the following. We perform PCA of the complete data. And then we retrain the first m components of the PCA by back projecting into the original space. Then we project the imputation into the PCA space, and then we update the imputation using the back projection, right, of the value into the original space. Very good. Some more interpretation of PCA. So these slides you have to, you have to convince yourself of this idea of a subspace in which you have most of the variability. Okay, so the more images you see, the better you get used to this sort of geometrical interpretation of the data. Okay, so again, three-dimensional data. The idea is that we want the PCA to have dimension 2. So in this three-dimensional space, the PCA will be a hyperplane of dimension 2. So a plane, and the idea is that the plane is the plane which is closest to the data in 3 dimensions, meaning as follows. You have this cloud of data in 3D. You want to slice it through using a plane of dimension 2, so that the distance from the points to the plane is minimized. As we said, distance is very, as a geometrical meaning that you study in high school, mean that you have your plane, you take the point, and then you take a line which is orthogonal to the plane, and you cross it a point with this line. This will give you a distance. You take the distance square, so you take this distance in the Euclidean sense, and then you sum over all the possible points, and this will be your overall distance, the distance between the set of points and a two-dimensional plane in this figure. So what you want to do is that you want to move the position of the plane in the three-dimensional space, so that when you look at this distance, this is minimized. This seems completely unrelated to SVD and eigenvalues, eigenvectors, but in reality, it is the same. It's the same concept, right? It's really the solution of this minimization problem, or this distance minimization problem, is expressed to SVD, to singular value decomposition. The reasons are purely mathematical, and they are beautiful in many aspects, but it's not a discussion of today. But you could write a proof that shows that minimizing the distance between the points and the plane yields a solution, which is the PCA result, right? So you do eigenvalue decomposition, you do singular value decomposition of X transpose X. You take the largest components, you use those components to play. Beautiful. Good. Matrix completion is another application of PCA, which is suitable for imputation data which is missing at random. Remember that we had this big discussion of imputation and what is the various ways in which data can be imputed, and we discussed imputation at random then. Good. This is another approach that was using recommender systems. So this goes back to your challenge number 1. So now we have N times P matrix, which is the movie rating in Netflix. And we have some data which is present when a certain person reviewed a certain movie, but we want to guess, right, how a certain person will rate a movie that they have not seen. This is because we're doing a recommender system. Very good. And yeah, that's it. That's it for now. That's it. There is a nice link to a book, and the book is about matrix completion algorithm that they use in the PCA. Okay, very good, guys. I think this is all I want to cover for today. Let me know if you have any questions or any queries. Otherwise, we go ahead and so we do is that yeah, next week we have the final presentation. Please try to do a good job. As I said, I was debating whether I should do I should do linear regression for only positive data or for periodic data. So what you guys are going to do now, it's for positive data. So trying to do linear regression for counts. So this is this Poisson regression. I'll try to hook up something for seasonalities and periodic data, because often when you work with, let's say, environmental measurements or natural science data, there is some sort of periodicity that occurs in the data. So I'll try to cook up something in the next challenge that has to do with this. I think it's very nice. And otherwise, as usual, I'm going to stop recording. I'm going to be here for a while if you have any questions. Otherwise, I'll see you guys next week. Okay? Ciao, guys.